In this video, I'm going to go through one of the examples in the Mom Practice computer homework. So I have selected question 2. Your question 2 should look pretty similar. And it says that we have a function right here. It's a third degree polynomial. They've given us the function and asked us to find the local minimum and local maximum. So you're going to find them. You're going to put in the x and y value for the minimum, the x and y value for the maximum. But when you do your written homework for Unit 3, Block 1, you will also be asked to do a formal write-up of how do you find the local minimum and maximum? How do you use calculus to really prove that they are minimum and maximum? So I'm going to go through that process and write it up nice and formally so you see what I'm expecting. All right, so over in Word, I have already written out the function. There's our function, and I'm telling you that we're going to find the local max and min points. So the first thing I would make note of, if you're finding local maximum or local minimum points, we know local max and local min points occur at critical points. Always. If it's a local max or min, it must be a critical point. So we need to first identify places that are critical points on f of x. So you ask yourself, what does it mean to be a critical point on f of x? F of x has a critical point at all the points where f prime is 0 and points where f prime is undefined. So I need to find f prime of x, and then I'm going to look at f prime of x and see, are there any places where f prime is undefined? And then I'll need to solve for the places where f prime of x is equal to 0. A derivative function is a second degree polynomial, a parabola, and the original f of x function was a third degree function. So we're trying to find where f prime of x is undefined or where f prime of x is 0. I will note f prime of x is never undefined because f prime of x is a second degree polynomial. It's a parabola. Remember, quadratic functions, parabolas, are defined for all x's. Their graph exists everywhere from left to right. You can plug in any x into the function and get a real valued output. So it's never undefined. There's no x you can plug in and get an undefined answer out. So there aren't going to be critical points of that variety. Now I'm going to solve for where f prime of x is equal to 0. This will be places where f of x is flat for an instant. These will be possible max or min. Okay, so I'm going to set f prime of x equal to 0. Quadratic function set equal to 0. To solve this quadratic function, you can use the quadratic formula. You could also use Excel to solve this using Solver, but I'm going to go ahead and show you how to do it by hand with the quadratic formula. Recall the quadratic formula is x equals negative b plus or minus square root of b squared minus 4ac all over 2a. So we're going to take that formula and we're going to plug in our coefficients a, b, and c, and we're going to solve for the value of x that makes our function equals 0. It's negative b, so that's negative 78, plus or minus b squared, so that's 78 squared, minus 4 times a times c, so that's 4 times negative 6 times negative 216 over 2a, and that would be 2 times negative 6. I'm going to just use Excel in this case to help me actually calculate this mess. So recopying here, negative 78 here. And the bottom 2 times negative 6 is really just negative 12. And what I'm going to do is I'm going to use Excel to help me calculate this number, 78 squared minus 4 times negative 6 times negative 216, the number underneath the radical. That's the discriminant. So in Excel, I'm going to type equals 78 raised to the second minus 4 times negative 6 times negative 216. B squared minus 4 times a times c. And it's 900. So the number underneath the square root is 900. So I simplified that quadratic formula calculation to this. All right, and now I could take the next step of actually performing the calculation. So the first one will equal negative 78 plus square root of 900. Notice you can type square root by typing SQRT and then put the value in parentheses. I press enter. That's the numerator. I need the whole calculation to equal this numerator divided by negative 12. So cell above it divided by negative 12. So one x value answer is x equals 4. But remember, there's two answers here. There's negative 78 plus square root of 900 over negative 12, and then there's negative 78 minus square root of 900, and equal that divided by negative 12. So the other answer is 9. So the two solutions to this are x equals 4 and x equals 9. I did my calculation, I showed my work. Now I'm going to actually write a sentence to explain what I just learned. What I just learned is that f of x has two critical points at x equals 4 and at x equals 9, where f of x flattens for an instant. Remember, what our ultimate goal here is to find local maximum and local minimum. All we've done right now is find critical points, but these are the two places that are potential maximum and minimum points. Remember, you cannot just jump to the conclusion that they are maximum. You actually have to now test those two values to see if they are local maximum and local minimum points. We're going to use the first derivative test to test them. So if you were drawing it by hand, you might draw out your number line, and then on your number line, you would put these in order. So I'm going to put like x equals 4 about here, and I'll note x equals 9 is up a little higher. I've kind of separated it out. These are numbers below 4, these are numbers between 4 and 9, and these are numbers above 9. And what we're now going to do is we're going to pick x's on these intervals, plug them in to f prime, and see the value of f prime. It doesn't matter what numbers you pick, just make sure they're on that interval. So for example, f prime of 3, that's a number below x is 4. And then I'm going to pick a number between 4 and 9, so maybe f prime of 6, just any number between 4 and 9. And then I'll pick a number above x equals 9, f prime of 10. We're going to plug these into the derivative function, and I'm just going to do it all at once in Excel. And another reason to do it in Excel is because if you create the nice input-output table, you'll also be able to check your overall conclusions by making a little graph on Excel when you're done. So here's how I do it. I come on over here to Excel, and I pick some x values that span to include x is 4 and x is 9. So I happen to go from x is negative 5 up to 14. Definitely includes 4 and 9. I, in column B, put f of x in there. So there's our original f of x function, that third degree function. Okay, we'll be able to graph that when we're done and take a look at our maxes and mins. I then added a column C where I have the derivative function. There it is, negative 6x squared plus 78x minus 216. Notice here at x equals 4, the derivative f prime is 0. Notice here at x equals 9, the derivative is 0. I went off to the side and I kind of merged some boxes together so I can make some conclusions for myself off to the side. Here at x equals 4 is a critical point where f of x is flat. And I'll note the same thing down here at 9. X equals 9 is a critical point where f of x is flat. I'm just going to note some other things. Notice this entire interval from x equals negative 5 to x equals 3, for all of these x's, the derivative is negative. And in fact, if you picked any x at all, if I change these to things like 3.9, the derivative would still be negative. If you picked negative 100, the derivative is still negative. Any x value below x is 4 will produce a derivative that's negative. Let me just put that in here. For x less than 4, we see that f prime of x is negative, so that tells us that f of x is decreasing for x less than 4. So that's what we're doing down here when we did our first derivative test. When we plug in a number below x is 4, we see f prime is negative. Prime of 3 in particular is negative 36. That's true for all x's on this interval. That means for all x's on this interval, f is decreasing. Notice the things I'm including in my description. F prime of 3 is this number. F prime is negative. F is decreasing. Then we move on to the next interval. F prime of 6. Again, let's go back to our Excel table. Here is x is 6. We see f prime is equal to 36. F prime of 6 equals 36. I don't particularly care about the fact that it's 36. What I care about is that f prime is positive, right? You'll see that's true for all x values on this interval between 4 and 9. So 4 less than x less than 9, we see that f prime of x is positive. So that tells us that f of x is increasing for this interval between 4 and 9. So again, over here on my Word file, f prime of 6 is 36. On that entire interval, f prime is positive. So on that entire interval, f is increasing because f prime is positive. Then we check this last interval, the interval for the x's above 9. Again, we go back to the Excel file. F prime of 10 is negative 36. F prime of 10 equals negative 36. What I'm really interested in the fact is that f prime is negative on this interval. So for x greater than 9, we see that f prime of x is negative. So that tells us that f of x is decreasing for this interval where x is greater than 9. So back to my Word file, f is increasing on this interval. So if you can imagine this, it's f decreasing, then f flat at x is 4, then f increasing. That means x equals 4 is a local minimum. It's decreasing before it, it's increasing after it. So it's down and back up. And we can now conclude, if you look at x equals 9, on the left side f is increasing, then it flattens at x equals 9, then, oops, I wrote here, increasing, my fault, and then it's decreasing. Remember, decreasing, I just wrote it wrong. So it's increasing on the left, and at x equals 9, it flattens, and then after x equals 9, it's decreasing. So that means x equals 9 is a local maximum. So we should see a function f that goes down, reaches a little low point, goes up, reaches a high point, and then comes down again. And if we were to graph, I'm going to highlight these x's and f of x's and make a little graph. There it is. Here is x equals 4, the minimum, and here is x equals 9, the maximum. If you want to zoom in on that more, we could just maybe go from 2 up to 11. Just going to highlight those points only. You get a little bit more zoomed in part of the graph, a little more clear. X equals 4 is the low, x equals 9 is the high. And you can see that on the graph, but really from the graph, you can't quite tell that it's exactly 4 and exactly 9. It could very well be 3.9 or 4.1 or 3.99 or 4.02 or something. You can't really tell from a graph. You can just get an estimate of the min and max. But using calculus, we solved and found there's a critical point at 4, a critical point at 9. That's the only critical points. Before it, f prime's negative. After it, f prime's positive. And after 9, it's negative again. We've proven with calculus that this is where the local max and min occur. All right, lastly then, the actual points where this occurs. When x is 4, I see that the value of f of x is negative 362, the y value. So at the point 4, comma, negative 362, we have a local minimum. And at the point 9, comma, negative 237, we have a local maximum. So now we can go into our MyOpenMath problem. And it says there's a local minimum when x is 4 with a y value of negative 362. And it says there's a local maximum at x equals 9 with a y value of negative 237. I hit submit, and it says yes. Good, correct, and accurate.